The sun doesn't usually fire twice from the same spot in one day. On April 24th, 2026, it did. An X 2.4 at 1:07 UTC. An X 2.5 7 hours and 6 minutes later. Same region. Escalating. And while all of that was happening, Earth itself started shaking. 5 magnitude, 5+ earthquakes in 24 hours. Crete, Kamchatka, the Aleutians. Coincidence? Probably. Probably. But I want you to stay with me, because there's a region rotating into view right now, behind the one that just fired. It's bigger, it's more complex, and it's aimed in a direction that changes everything about what comes next. Before we get into it, if you are new here, hit like and subscribe to The Quiet Archivist. Because we are tracking every piece of this, the forecast that quietly flipped overnight, the signatures the headlines left out, the earthquakes that shook the planet in the same window the sun fired twice, and the region rotating into view right now that is bigger than the one that just went off. If something is actually building here, you will want to be here when it happens. Now settle in and let's get into it. At 1:07 UTC on April 24th, 2026, the sun did something that most people on Earth will never hear about. It fired. A hard, clean X 2.4 flare erupted from a region cataloged as 4419, a spot that had been quietly rotating toward the western edge of the solar disk for days. It was the kind of blast that triggers what forecasters call an R3 strong radio blackout. The kind of event that makes shortwave operators across the sunlit half of the planet suddenly hear nothing but hiss. And then, 7 hours and 6 minutes later, the same region fired again. Only this one was bigger. An X 2.5. Same spot. Escalating intensity. Back to back, from a single active region that was supposedly on its way out of view. Now, if you were watching the initial reports, you saw something very specific. NOAA's first read on the coronal mass ejection, the giant cloud of charged plasma launched by that first flare, came back reassuring, mostly northwest trajectory. In plain English, that means the cloud was thrown off to the side, angled away from us, expected to sail harmlessly past our planet. A miss. And for about 12 hours, that was the story. That was the headline, if anyone even bothered to write a headline. Then the forecast changed. Quietly, without fanfare, without a press release, the Space Weather Prediction Center revised its language. The new version used the phrase Earth-directed component possible, late April 25th into early April 26th. Both statements, the first and the second, are technically correct. They just describe two different versions of reality, separated by a handful of hours of new data. And while that was happening, a second CME was still being modeled. A Type 2 shock front was clocked screaming outward at 1,293 kilometers per second, and a 10-centimeter radio burst spiked to 570 solar flux units. A Type 4 emission, the kind tied to serious radiation events, lit up the spectrum like a warning flare. So how exactly does a miss become a possible hit? To answer that, you have to see what the models saw, and more importantly, what they didn't. Here's something the average person never really thinks about. Space weather forecasts are not announcements. They're conversations. The Space Weather Prediction Center, a small but very serious branch of NOAA based in Boulder, Colorado, doesn't issue a prediction and then walk away. They update. Constantly. Every few hours, sometimes every few minutes, as new data rolls in from coronagraphs, satellites, and magnetometers scattered across the solar system. What you see in the news is a single frozen frame from a movie that's still being filmed. Think of it like hurricane tracking. When a storm forms in the Atlantic, the forecast cone shifts over days. The track wobbles. The intensity climbs or drops. The public understands that because hurricane coverage is everywhere, constant, dramatic, narrated by meteorologists on television for a week at a time. Solar storms don't get that treatment. There's no 10-day forecast crawl at the bottom of the screen for plasma clouds. There's no anchor standing in front of a green screen pointing at a swirling sun. The coverage, when it exists at all, is a single headline, often written hours after the event, and then silence. The real audience for these forecasts isn't you. It's satellite operators deciding whether to reorient their spacecraft. It's airlines rerouting polar flights. It's power grid managers in high-latitude regions watching their transformers. These are operational updates, not stories. They're not designed to be dramatic. They're designed to be correct. And that creates what I'd call a hidden second timeline. Timeline A is the public version, the one-line summary, the reassuring miss. Timeline B is the evolving scientific model, shifting and refining behind the scenes. Most of the time, those two timelines stay close enough that nobody notices the gap. But every so often, an event exposes it. This is one of those events. The revision itself wasn't rare. What was rare is that you're seeing it happen. You were told one version. The system had already moved on. And the reason it moved on comes down to something very specific about where this flare actually happened. Region 4419 didn't fire from the middle of the sun. It fired from the edge, specifically from around 16 degrees north latitude, 68 to 70 degrees west longitude, right up against what astronomers call the western limb, the rim of the visible disk. The place where, from Earth's perspective, the sun's surface curves away from us and disappears. That geometry matters more than you might think. Imagine standing next to a thunderstorm. If you're directly underneath it, you can see the full structure, the anvil, the rain shaft, the lightning core. If you're watching it from the side, miles away, you see a silhouette. You see the edge. You cannot tell how wide it is in the direction pointing toward or away from you. That's exactly what happens with a limb flare. We're watching the eruption sideways. Our instruments, the coronagraphs aboard spacecraft like SOHO and stereo, produce two-dimensional images of a three-dimensional event. Depth is a guess. When a coronal mass ejection launches from near the limb, several things get harder. Figuring out its true width gets harder. Figuring out its true direction gets harder. Figuring out whether any part of it is actually aimed at Earth gets significantly harder. A huge percentage of misclassified CMEs in the historical record came from limb events, simply because the angle was bad. You're trying to judge the aim of a cannon from directly beside the barrel. Good luck. And then there's the concept of a halo CME. When a plasma cloud is aimed at Earth, it appears to expand outward in every direction around the sun, forming a ring, a halo. Full halos are obvious. Partial halos are tricky because the Earth-directed portion might be faint, overlapping with brighter material moving sideways. Early imaging of Region 4419's eruption was dominated by that bright northwest plume. It looked like a clean side shot. Only later, as more frames came in, did a broader, subtler structure start to emerge underneath it. A bad angle makes for a bad first read, and then the second flare made everything worse, because the second event confirmed that something much larger had actually been launched. At 0813 UTC, the same region fired again, X 2.5, slightly stronger than the first. But the real story wasn't the X-ray intensity. It was everything else that came with it. Because when that second flare peaked, instruments all over the sunlit hemisphere of Earth started picking up signatures that told a very particular story. Signatures that confirmed this wasn't just a flash of light. This was mass. Moving fast. The first signature was a Type 2 radio burst. That's a specific kind of emission, produced when a shockwave rips through the solar corona, compressing plasma as it goes. generating radio waves at characteristic frequencies that drift lower over time. Translation: something big was moving outward at high speed, punching through the sun's atmosphere like a bullet through fog. The shock front was clocked at 1,293 kilometers per second. That's roughly 2.9 million miles per hour, fast enough to cross the distance between the sun and Earth in under 2 days. Then came the Type 4 emission. These are long-duration radio signals produced by electrons trapped in the magnetic loops of a major eruption, spiraling and radiating for minutes or even hours after the initial flash. Type 4 emissions are the ones solar physicists associate with serious events. The kind that can produce radiation storms. The kind that matter. And layered on top of all that was the 10-centimeter radio burst itself, peaking at 570 solar flux units. A solar flux unit, or SFU, is a measurement of radio intensity at a specific frequency. Normal quiet sun background hovers around 128 SFU. So 570 is roughly 4.5 times the baseline, for about 6 minutes. Short, but intense. And during those 6 minutes, GPS signals can jitter, radar systems can get noisy, satellite communications can pick up interference. Not theoretical. Real systems, real disruption, real consequences. Combine all three signatures, Type 2, Type 4, and a half-kilowatt radio burst, and what you have is the unmistakable fingerprint of a significant CME. A big one. And something was already on its way. So let's pull back for a second. How does a forecast go from miss to possible hit in 12 hours? It's not a conspiracy. It's not incompetence. It's not even unusual once you understand how these models actually work. Space weather forecasting is probabilistic. That's the single most important thing to understand about this story. Every forecast is a spread of possible outcomes, not a single answer. Early in an event, when data is scarce and the CME is still close to the sun, that spread is enormous. The cone of uncertainty is wide. Earth might be inside the cone at low probability, or outside it entirely. As time passes, as more coronagraph frames arrive, as solar wind monitors start to pick up density and speed changes, the cone narrows. What was low probability becomes higher probability. What was outside becomes inside. The event itself didn't change. The confidence in our estimate of it did. But that's not how it feels. From the outside, it feels like the story reversed. It feels like someone got it wrong, or changed their mind, or is hiding something. None of that is true. The model just got better information, and it adjusted. That's the job. That's what a good forecast does. And here's where this story stops being about a single flare. Because while Region 4419 was firing, another CME, launched on April 23rd, was already traveling outward through the inner solar system. 2 plasma clouds, same rough direction, different speeds, different launch times, and a growing possibility that they interact. Is this still one event? Or is something more complicated happening? Something the forecast isn't fully capturing yet. And then there's the other pattern, the one nobody's officially talking about. Because while the sun was active, Earth was active too. 5 magnitude, 5+ earthquakes in the same 24-hour window. Crete, Kamchatka. The Aleutians, not proven to be connected, but it's a pattern worth noticing. The real story here isn't what already happened, it's what happens next. To understand why a forecast can flip direction, you have to understand what a CME actually looks like when it launches. And, just as importantly, what it looks like to us while it's launching. Because those two things are very different. A coronal mass ejection is a 3-dimensional cloud of magnetized plasma. Billions of tons of it, roughly the mass of a small mountain, flung outward at speeds that can exceed 3,000 kilometers per second. It has structure, a leading edge, a cavity, a dense core. It rotates, it expands, it interacts with the solar wind it moves through. It's a living, evolving object, and the only way we see it from 93 million miles away is through instruments called coronagraphs. A coronagraph works by blocking the bright disk of the sun itself, creating an artificial eclipse so that the faint outer atmosphere, the corona, becomes visible. When a CME erupts, it appears against that darkened background as a ghostly, expanding shape, brightening and drifting outward over minutes and hours. But here's the catch. Those images are two-dimensional. They're flat projections of a three-dimensional cloud. Depth is inferred, not measured directly. Even with two coronagraphs at different angles, like the old stereo mission used to provide, the reconstruction is an approximation. Early frames make this worse. The first few images after an eruption are low in contrast because the CME hasn't expanded far enough from the sun to be clearly visible against the coronal background. Speed is a guess from 2 or 3 data points. Direction is inferred from the apparent center of expansion, which can be badly skewed by projection effects. Width is a range, not a number. Models take all of this, all of it uncertain, and produce a forecast. The first forecast is essentially a very wide probability cone, a best guess based on thin data. It's like predicting where a hurricane will make landfall using only the first 2 satellite images after formation. The model didn't fail, it just started incomplete. And in this case, one specific scenario explains almost everything about why the forecast flipped. A halo CME is one where the ejected cloud appears to expand in every direction around the sun, forming a glowing ring. When you see a full halo in a coronagraph image, it means the CME is aimed almost directly at you, because you're looking down its throat. That ring is the cross-section of a cone pointed at Earth. It's unmistakable. And, for forecasters, it's terrifying in the best possible way, because it removes almost all directional ambiguity. Partial halos are different. Partial halos are when only part of that ring is visible, usually because the CME is angled off-center, or because parts of the ejected structure are fainter than others. And here's where things get interesting with Region 4419. The early imaging was dominated by a bright northwest plume. That plume was obvious, fast, and clearly pointed away from Earth. It captured the forecast. It drove the first classification, mostly northwest. A miss. But a CME isn't a bullet. It's a cloud. And clouds have edges. If an Earth-directed component existed at launch, fainter than the dominant plume, overlapping with it on the near side of the sun, it might have been completely invisible in those first frames, drowned out by the brighter sideways motion, lost in the noise, a flashlight beam, and a wider, dimmer glow around it. You see the beam first. The glow takes longer to register. As more frames came in, as the expanding cloud moved farther from the sun and spread out, that symmetry started to become visible. The outline of a structure broader than the initial plume, possibly a partial halo, emerging slowly from behind the brighter material. And once that shape started to resolve, the models had no choice but to update. This is a known scenario in CME analysis. It's documented, it's expected, but it's rarely noticed by the public because the public only sees the first version. What you see first isn't always the full structure. And then, as the data improved, the models did something very specific. They tightened. Modern space weather forecasting doesn't run a single simulation. It runs dozens, sometimes hundreds. Each one uses slightly different input assumptions, a different launch speed, a different angle, a different width, a different magnetic orientation. Collectively, they're called an ensemble, and the output isn't a single prediction. It's a cloud of possible futures, each weighted by how likely its inputs are given the observations we have. Early in an event, the ensemble spread is enormous. Some simulations have the CME missing Earth entirely. Some have a glancing blow. A few have a direct impact. The probability at any single location, including Earth, is often low because the total probability is spread across a very wide cone of outcomes. That's what produced the first forecast. In the ensemble, Earth was within the possible range, but only at low probability. The dominant solutions had the clouds sailing past to our north and west, so the headline was mostly northwest trajectory. A miss. Then the data got better. New coronagraph frames arrived. Maybe solar wind data from upstream spacecraft started showing early disturbances. Maybe the stereo-like viewpoints helped constrain the true angle. With every new data point, the ensemble tightened. Simulations that didn't match the new observations got down-weighted. Simulations that did got up-weighted. And as that process repeated, the spread of possible outcomes collapsed. It narrowed. And in this particular case, the narrowing happened in a direction that brought Earth from the edge of the probability cloud to somewhere closer to the middle. Earth wasn't added to the forecast. Earth was always there. It just became more likely as the model learned. This is the thing binary language hides. Hit or miss. Yes or no. Real space weather isn't binary. It's a continuous probability spectrum, shifting in real time. The event didn't change. The confidence did. And here's the thing. This has happened before. Many times. You just weren't looking. Forecast revisions of this kind are part of the historical record. They go back as long as we've been watching the sun with coronagraphs. Arrival time predictions for CMEs routinely shift by 7 to 12 hours as an event unfolds, sometimes more. Events initially classified as weak glancing blows have occasionally produced stronger than expected geomagnetic storms, when the magnetic orientation of the cloud turned out to be more favorable than models assumed. And events initially classified as major threats have sometimes fizzled on arrival because the internal magnetic structure rotated in a way the models couldn't predict. The most famous near miss in modern history was the July 23, 2012 event. A truly enormous CME, fast, dense, with a strong embedded magnetic field. It crossed Earth's orbit. It just happened to do so about a week after Earth had already moved past that particular point in space. If it had launched 9 days earlier, it would have hit us directly. Estimates of the geomagnetic storm it would have produced have been argued about for years, but the lower end of those estimates is serious. The upper end is grid-threatening. Nobody saw that CME in the news cycle. Because it missed. The public never knew. The scientists did. Forecasting has improved since then. Better coronagraphs. Better solar wind monitors at the Lagrange points. Machine learning models that can integrate data faster than any human analyst. But the fundamental limitations remain. LIM events are still hard. Fast CMEs are still hard. Multiple overlapping CMS are very hard. And this current event, Region 4419's double flare on April 24th, fits the known pattern of forecast revision almost perfectly. It's not unprecedented, it's textbook. The combination, though, is what makes it interesting, because now there's more than one CME in play. The core message of this entire act, if you take nothing else, is this. Forecasts resolve. They don't reverse. What looks like a contradiction from the outside is almost always a refinement from the inside. The story didn't change. The focus got sharper. Always expect updates. Always assume the first version you heard is incomplete. Always give the models room to learn. And here's the part that matters for what comes next. A previous CME, launched on April 23rd, is already traveling through the inner solar system on its own trajectory, with its own arrival window. Now this newer, faster CME from region 4419 is barreling outward behind it. Two clouds, same general direction, different speeds. The faster one can potentially catch the slower one. And when CMEs catch each other, the physics gets interesting. Compression, magnetic field interactions. Possibly something forecasters have a very evocative name for. Cannibal CME. Something else was already on the way, and the way it arrives, or doesn't, could change everything. Before Region 4419 fired, the Sun had already let one go. On April 23rd, a coronal mass ejection launched from a different part of the disk. Slower, smaller, relatively uneventful. It was tracked. It was modeled. It was expected to produce, at most, a minor geomagnetic disturbance on arrival. Maybe a G1 storm. The kind of thing that causes auroras at high latitudes and barely a blip in anyone's systems. A background event, in other words. Nothing to write home about. Under normal circumstances, that would have been the end of the story. The cloud would sweep past Earth, maybe graze the magnetosphere, maybe produce some pretty lights visible from northern Scandinavia, and then continue outward into the solar system to fade into the background solar wind. End of file. But these aren't normal circumstances, because now there's a second CME behind it. Faster, denser, launched from a region that was already one of the most active on the disk, and the geometry of the inner solar system is about to get crowded. When you launch a fast CME into the wake of a slower one, several things can happen. The first, and most common, is nothing. The fast cloud simply catches up, passes through the turbulent wake of the slower one, and continues on its original trajectory with minimal modification. The solar wind is a thin environment. Interactions aren't guaranteed. The second possibility is that the faster cloud plows into the back of the slower one, compressing itself, and arriving at Earth as a single, merged structure, with properties that neither original cloud possessed alone. Denser, faster, more magnetically complex, potentially more geo-effective. And the third possibility, the most interesting one, is what solar physicists have come to call a cannibal CME. A scenario in which the faster cloud doesn't just pass through or merge with the slower one. It consumes it. The two structures tangle, their magnetic fields reconnect, and the combined object that arrives at Earth is something new. Something the original forecast never described, because the original forecast was modeling them as separate events. Let's slow down on this, because it matters. When two CMEs interact in the inner solar system, the first thing that happens is compression. The faster cloud's leading edge rams into the slower cloud's trailing edge. Plasma piles up. Density increases, sometimes by factors of 2 or 3. The magnetic field, which was already structured and embedded in each cloud, gets compressed along with the plasma. And a compressed magnetic field is a more intense magnetic field. Stronger interactions with Earth's magnetosphere upon arrival. The second thing that happens is magnetic reconnection. When two magnetized plasma clouds push against each other, their field lines can tangle and, in some configurations, snap into new arrangements, releasing energy and reorganizing the overall structure of the combined cloud. This is the same fundamental process that powers the flares themselves, just on a slower, quieter scale. The result is that the merged CME may have a completely different internal magnetic orientation than either of the originals. And that orientation is the single most important factor in determining whether a CME produces a major geomagnetic storm on Earth. Specifically, it comes down to a parameter called BZ. BZ is the north-south component of the magnetic field inside the cloud. If BZ is positive, pointing northward, the cloud's magnetic field aligns with Earth's own field, and the interaction is relatively gentle. The cloud deflects around us. Auroras are modest. systems stay calm. But if BZ is negative, pointing southward, the cloud's field opposes Earth's field. They reconnect. Energy pours into the magnetosphere. Auroras intensify. Currents flow through the upper atmosphere. Power grids at high latitudes start to feel it. The current forecast for the April 25th into April 26th window is modest. G1 level, minor storm conditions. Aurora at high latitudes, minor fluctuations in weak power systems. Nothing that should alarm anyone. That forecast, though, assumes the two CMEs arrive separately or interact minimally. If the interaction is more complete than expected, if the merger produces a strongly southward BZ, the arrival could significantly exceed the forecast, not into catastrophe territory, but into a category or two higher than what's currently on the board. Forecasting a single CME is hard. Forecasting two interacting CMEs is exponentially harder, because now the model isn't just tracking one plasma cloud through the solar wind, it's tracking two. It's trying to predict whether they interact, when they interact, where they interact, and what the interaction does to the combined structure. Each of those is its own uncertainty. Stacked together, they multiply. The April 23rd CME's exact speed and trajectory carried their own error bars. The April 24th CME's speed and trajectory carry even larger error bars because it's newer, and as we've already discussed, it launched from near the limb. Combining two uncertain objects and asking the model to predict their interaction is genuinely difficult. The best models available, running on supercomputers at NOAA and NASA and various international centers, can give probability distributions for various outcomes. But those distributions are wide, wider than the public would be comfortable with, if anyone ever bothered to show them. What forecasters do in practice is run the ensemble, watch for consensus, and issue the most likely outcome with appropriate caveats. Right now, the most likely outcome is a modest arrival. A G1 storm, possibly brushing into G2 territory if conditions align. But the tail of that probability distribution, the part that represents less likely but still possible outcomes, extends further, into G3. Theoretically, in the most unfavorable interaction scenario, even further. Nobody's forecasting that. But the possibility is inside the cone. The window to watch is late April 25th into early April 26th. That's when the first arrivals are expected. The second cloud, if it arrives separately, could come a few hours later, or it could already be merged with the first. Watch the solar wind monitors at the L1 Lagrange point, about 1 million miles upstream of Earth. When a CME passes those instruments, we get roughly 30 to 60 minutes of warning before impact. That's the final, unambiguous, no more guessing moment. Everything up to that point is modeling. Everything after is physics. Here's something you might have missed in the initial coverage. The April 24th double flare didn't just produce CMEs, it produced signatures. Specific, measurable signatures that tell us something about the scale of what's moving through the solar system right now. We've already talked about the Type 2 shock clocked at 1,293 kilometers per second. We've already talked about the Type 4 emission. But there's more. The 10-centimeter radio burst hit 570 solar flux units. To put that in perspective, a typical quiet sun measurement at 10 centimeters runs around 128 solar flux units, so the burst was roughly 4.5 times baseline. For 6 minutes, the sun was radiating that much extra energy in a single radio band. 10-centimeter bursts of that magnitude are correlated, statistically, with significant CME launches and with potential radiation environment enhancement in the following hours. They're not causal. The radio burst doesn't cause the radiation. But they're linked because both are symptoms of the same underlying event, the same magnetic eruption, and the electron flux at geostationary orbits spiked. 3,446 particle flux units. That's a meaningful number because elevated electron flux at high orbits means satellites are sitting in a more energetic environment. Spacecraft charging becomes a concern. Subtle electronic effects can accumulate. No single event is likely to be catastrophic, but over time, or in the wrong conditions, these are the kinds of signatures that operators pay attention to. All of this, the shock, the radio burst, the Type 4, the electron flux, paints the picture of an event that is larger and more energetic than the initial headline suggested. The first forecast said mostly northwest trajectory. The signatures say that whatever direction the cloud was headed, it was carrying a lot of energy. And if any meaningful fraction of that energy is pointed at us, even glancing, the arrival window matters. If you're following this event in real time, and I suspect some of you are, there are a few specific things to keep an eye on. First, the solar wind data at L1. When the speed jumps, when the density spikes, when the magnetic field rotates, that's your first unambiguous sign the CME has arrived. It'll happen late April, 25th, or early April 26th, if the current forecast holds. Watch the BZ component specifically. If BZ plunges south and stays there, the storm response on Earth will be stronger than the current forecast suggests. Second, watch for any further updates from SWPC. If the forecast upgrades from G1 to G2 or higher in the hours before arrival, that's the model seeing something in real-time data that wasn't visible in the initial projection. Third, watch the aurora reports from high-latitude regions: Scandinavia, Alaska, northern Canada, New Zealand. If aurora becomes visible noticeably farther south than usual, that's a direct indicator of enhanced storm conditions. And there's one more thing. Something the forecasts don't explicitly address, but which this whole situation hints at. The sun didn't just fire once. It fired twice. In the same region. In the same day. That's a pattern. That's a signal about the magnetic state of Region 4419, and maybe about the overall state of this stretch of the solar cycle. It's not the event. It's the setup. And while we've been looking at the sun, signals on Earth have been quietly stacking up too. Signals that, if you line them up next to the solar data, start to look suspiciously like they belong in the same story. Let's come back to that 10-centimeter radio burst, because it deserves more attention than it got. 570 solar flux units is the kind of number that, in operational space weather circles, triggers specific protocols. GPS operators pay attention. Radar operators pay attention. Satellite operators pay attention. But nobody outside those circles heard anything about it, because there's no dramatic public-facing alert for radio bursts. They happen, they disrupt systems briefly, and then they fade. Invisible to anyone not directly affected. For those 6 minutes, somewhere in the world, GPS receivers experienced degraded accuracy. Not catastrophic failure, just noise. Positional jitter. The kind of thing that doesn't matter if you're using GPS to find a coffee shop, but absolutely matters if you're using GPS to land an aircraft in zero visibility, or to precisely guide a surveying operation, or to coordinate time synchronization across a financial network. A 570 SFU burst in the 10-centimeter band is roughly the boundary where these effects become noticeable to operational systems. So this was that boundary, crossed for 6 minutes, on the sunlit side of Earth. And the Type 4 emission, the long-duration radio signature that persisted after the initial flash, is the specific marker that correlates most strongly with proton events. When a Type 4 is observed, the probability that energetic protons will arrive at Earth in the following hours or days increases noticeably. Not every Type 4 produces a proton storm. Most don't. But the correlation is real, and it's the kind of thing that makes radiation specialists start watching specific instruments more carefully. None of this means anyone should panic. The radiation environment from this particular event has been elevated, but not extreme. The immediate effects have been minor, but the signatures, stacked together, tell you this wasn't a small event. It wasn't a hiccup on the sun's surface. It was a major release of energy, and we're still waiting to see how much of that energy finds its way to Earth. There's another number worth understanding: 3,446 particle flux units. That was the electron flux measured at geostationary orbit in the aftermath of the April 24th flares. Geostationary orbit is where a lot of our communications and weather satellites live, about 36,000 kilometers above Earth's equator, far enough out that they orbit in sync with Earth's rotation and appear fixed in the sky from below. When the electron flux in that region spikes, what you get is a phenomenon called spacecraft charging. It works like this. Energetic electrons accumulate on and inside satellite surfaces and components. Different parts of the spacecraft, insulators and conductors, accumulate charge at different rates. The voltage difference between them can build up until, suddenly, a small electric discharge arcs across the satellite. That discharge can disrupt electronics. It can corrupt data. In rare cases, it can damage components permanently. Operators mitigate this with specific design choices and operational procedures, but the risk doesn't go to zero. It just gets managed. A 3,000 plus particle flux unit environment is elevated. Not extreme, but elevated. Elevated enough that operators of satellites in that orbit region were likely watching their telemetry more carefully than usual over the past few hours. Elevated enough that any satellite running near its design margins was statistically more likely to experience an anomaly. These anomalies are often minor and go unreported to the public, but they happen continuously across the fleet of thousands of satellites currently in orbit around Earth. The electron flux is one of the invisible things that shape the reliability of the modern world, and it's been up, quietly. There's a pattern emerging on the sun right now that, if you step back and look at the whole disk rather than just one region, starts to feel less like a series of isolated events and more like a coordinated performance. Region 4419 fired twice on April 24th. Region 4420, even larger and more magnetically complex, is rotating into firing position behind it. Region 4423 emerged fast, went from nothing to a recognized active region in a matter of hours. And the overall flare index has been elevated, with multiple M-class events in the background that didn't even make the main news cycle. What you're looking at is a distributed state, not one hot region surrounded by a quiet sun. Multiple active regions, at different longitudes, different stages of development, different magnetic classifications, all contributing to a generally elevated solar baseline. This is what solar maximum looks like up close. Not a single catastrophic event. A drumbeat. Persistent. Spread across the disk. Overlapping. And this matters for forecasting because it changes the statistical background. When the sun is generally active, the probability of any given hour producing an M-class or X-class flare goes up. The probability of overlapping CMEs in the inner solar system goes up. The probability of compound events, cascading signatures, and forecast revisions goes up. Everything becomes more interconnected. The individual events are harder to isolate, harder to model cleanly, because they don't happen in isolation anymore. What that produces, on the ground, is exactly what we've been seeing. Forecasts that shift, signatures that stack, events that seem to come in clusters rather than singly. It's the pattern of a star in a particularly noisy phase of its cycle. And while all of this was happening, while the sun was restless, something else was happening down here. Something that, at first glance, doesn't seem related. But maybe, if you squint, it does. Let's pause on something important. When the sun is in this kind of distributed, elevated state, the entire space environment around Earth shifts. It's not just about the occasional big flare, it's about the background. The solar wind speed is elevated. The interplanetary magnetic field is more complex, more frequently southward in orientation. The density of high-energy particles filling the space between the sun and Earth is up. All of it, slightly but persistently above the quiet sun average. This baseline shift has consequences. Atmospheric drag on low Earth orbit satellites increases slightly because the upper atmosphere expands when solar activity is high. Polar communication is more frequently degraded. High-frequency radio operators at high latitudes have bad days more often. Aurora reports extend to lower latitudes more frequently. The whole system is running, not in crisis, but in a slightly elevated state of alert. It's the background hum against which individual events are measured, and it's why, when an event like the April 24th double flare happens, the reaction from the scientific community is not surprise, it's recognition. This is what this kind of stretch looks like. This is normal for solar maximum, not quiet sun normal, but active sun normal. The patterns are known, even if the specific events are never predictable in detail. What we're living through is a statistically expected phase of the sun's 11-year cycle, happening with the usual mix of individual surprises and overall consistency. That context matters when we start looking at other things that have been happening at the same time. Things on Earth. While the sun was firing, Earth was shaking. 5 magnitude 5 or greater earthquakes in the same 24-hour window. Crete, Kamchatka, the Aleutians, plus a couple others. And I know what you're thinking, because I thought the same thing when I saw the list. The sun fires. The Earth shakes. Something must be connected. That's the intuition. And intuition is where a lot of bad science starts. But it's also where a lot of good questions start. So let's take this one seriously. Not because I'm claiming a connection. Not because the data proves a connection. But because the pattern is there. It's been noticed by people with legitimate credentials. And it's worth understanding what the argument actually is before deciding what you think about it. Because here's the thing. If there's a relationship, even a weak one, between solar activity and seismic activity, it would change how we think about both. It would mean that the space weather we're watching so carefully, the CMEs, the flares, the radiation storms, aren't just affecting satellites and power grids. They might, in some small way, be pulling at the ground beneath our feet. That's a big claim. Most scientists don't buy it. But the question has been around longer than you might think, and the evidence, for what it is more substantive than the usual fringe material. So let's actually look at it. Let's list the events clearly, so there's no ambiguity about what we're discussing. In the 24-hour window centered on the April 24th solar flares, the USGS earthquake catalog recorded the following significant events. A magnitude 5.3 off the coast of Crete in the eastern Mediterranean. A magnitude 5.6 near Kamchatka in the Russian Far East. A magnitude 5.1 in the Aleutian island chain off Alaska. A magnitude 5.0 in the southern Pacific. A magnitude 5.2 in Indonesia. 5 events above the magnitude 5 threshold in a single day, spread across roughly a third of the planet's surface. Now, here's the first thing to understand. Magnitude 5 earthquakes are not rare. The global average is about 1,500 per year, which works out to roughly 4 per day. So 5 in a day is above average, but not dramatically so. Statistically, a day with 5 M5 events is maybe the 80th or 90th percentile. Unusual, but absolutely within the range of normal variation for a quiet week, let alone an active one. If you picked any random day in the last few years and counted, you'd occasionally get days with 6, 7, or more. The baseline is noisy. But here's where it gets interesting. When you look at the specific distribution, the locations of the earthquakes, They trace a broad band across some of the most tectonically active zones on the planet. The Mediterranean Collision Zone, the Kamchatka-Aleutian Arc, the Indonesian Subduction Zone. These are the regions where tectonic stress is always high, where earthquakes are always possible, where small triggers can unlock accumulated strain. They're not random, they're primed. The question isn't whether these regions can produce M5 events on any given day. They can. The question is whether something about this particular day, with this particular solar event, tilted the probability one way or the other. To evaluate whether the solar seismic coincidence means anything, you have to know the baseline. How often do M5 plus earthquakes cluster in ways that look suggestive? The answer from seismology textbooks is often. Earthquakes are not evenly distributed in time. They cluster. Aftershock sequences cluster. Seismic swarms cluster. The background rate has quiet periods and active periods that bear no obvious relationship to anything external at all. So on any given day, if you're inclined to see a pattern, you can find one. Solar flares happen multiple times a month during solar maximum. Magnitude 5 plus earthquakes happen multiple times a day. The probability of both happening within the same 24-hour window is, on pure chance alone, very high. That's the first thing any serious analysis has to confront. The coincidence itself is not evidence of anything. It's noise. But there's a second layer. Several peer-reviewed studies over the past decade have looked at correlations between specific solar wind parameters and seismic activity, with mixed results. Some have found statistically weak, but apparently real correlations. Others have found nothing. The community is divided, and the mainstream position remains strongly skeptical, for good reason. The proposed mechanisms for a connection are all speculative. The physics is not well established. The effect sizes, even in the studies that claim them, are small. Extracting signal from noise in this area is genuinely difficult. What the studies have in common is that they all depend on how you define the windows, how you select the events, and how you handle the statistical corrections. Different choices produce different answers. That's not necessarily dishonest science. It's just a reflection of how hard the problem is. If there's a real effect, it's subtle. If there isn't a real effect, the data is consistent with that too. And we don't currently have the tools to resolve it conclusively. One of the more widely cited papers in this area is a 2020 study by Marchitelli, Ghosh, Galli, and co-authors, published in Scientific Reports. They looked at global catalogs of large earthquakes over a 20-year period and compared their timing to solar proton fluxes measured from space. Their claim was that they found a statistically significant correlation between high-energy proton bursts from the sun and earthquakes in the following 24 hours. The mechanism they proposed was speculative. They suggested that energetic solar protons could, under specific conditions, generate electrical currents in Earth's crust via something related to the reverse piezoelectric effect. The piezoelectric effect, in its forward direction, is what happens when you squeeze certain crystals and they produce a voltage. The reverse is what happens when you apply a voltage and the crystals deform. In principle, if solar-induced currents could flow through stressed rock formations, they might cause tiny deformations. And in rock formations already near the breaking point, those tiny deformations might trigger a slip that was going to happen anyway, just slightly earlier than it otherwise would. The paper got significant pushback from the seismology community. Other researchers pointed out statistical issues with the analysis, alternative explanations for the apparent correlation, and the implausibility of the proposed mechanism at the energy levels actually involved. But the paper wasn't retracted. It sits in the literature. And the underlying question, whether solar activity can nudge already primed fault systems into releasing stress slightly earlier than they otherwise would, remains unresolved. What's important to stress is that no one, not even the authors of that paper, is claiming that the sun causes earthquakes. Earthquakes are caused by tectonic stress. The stress builds up over decades or centuries, and when the rock can no longer hold, it fails. The sun doesn't create the stress. The question is only whether, at the very last moment, in faults that are already on the edge of failure, a solar-driven external influence could tip the timing. That's a much smaller claim than it might initially appear, and even in its smallest form, it hasn't been proven. There have been previous events where large solar storms occurred without any notable uptick in seismic activity, and there have been periods of intense seismic activity with a perfectly quiet sun. The record is full of counterexamples in both directions, which is, in itself, meaningful. It means that if there's an effect, it's either very weak or very specific, or both. It means that you can't point to any single event, including this one, and claim that it proves anything. The most honest way to describe what's happening right now is this. The sun is very active. Earth is experiencing a moderately active seismic day. Both things are true. Neither is evidence for the other. If there's a correlation, we won't be able to see it in a single event. It would require statistical analysis across thousands of events, with careful controls for all the confounding factors. And that kind of analysis, when it's been done rigorously, has produced results that are ambiguous at best. This is frustrating if you're looking for a clean story. There isn't one here. What there is a pattern that shows up often enough to keep researchers asking questions, and rarely enough that nobody's been able to nail it down. That's exactly what a genuinely open scientific question looks like when you're in the middle of it. Not a conspiracy. Not a breakthrough. A maybe. A maybe that keeps coming up and keeps not resolving year after year. And in a moment like the one we're currently living through, when the sun is firing and the earth is shaking in the same 24-hour window, you can see why the question refuses to go away. So here's where we land. The April 24th solar event coincided with a modestly elevated day of global seismic activity. Those two facts are both real. The relationship between them, if any, is not established. Saying so carefully, rather than either dismissing the coincidence outright or inflating it into a mystery, is the honest way to cover this story. What I can tell you is this. If you're the kind of person who likes to keep an eye on patterns that mainstream science hasn't fully resolved, this is one to watch. Not because I can tell you it means something, but because, over time, across many events, if there's a real signal in this data, it'll emerge. It won't emerge from this week. It'll emerge from decades of careful statistics. And you, by paying attention now, are part of the informal network of curious people who eventually make those datasets worth analyzing. So, the sun fired, the earth shook. The two facts sit next to each other. Neither requires the other to be interesting. Both, together, are a little harder to dismiss than either one alone. Make of that what you will. And while we've been looking back at what already happened, something bigger has been quietly rotating into view. Something that might make all of this look like a warm-up. Here's the thing about Region 419. By the time you're hearing this, it's almost gone. The sun rotates on its axis roughly once every 27 days as seen from Earth. Sunspots and active regions ride that rotation, appearing first on the eastern limb, marching across the visible disk over about 2 weeks, and finally rotating off the western limb and disappearing from our view. Region 419 has been on its exit leg for days. The April 24th double flare was, in a very real sense, its farewell performance. That doesn't mean the region is gone. It's still there, still active, just on the far side of the sun now, invisible to our direct imaging. It'll continue to do whatever it's going to do, producing flares or decaying or restructuring until it eventually rotates back around to face us in about 2 weeks. If it's still active when it returns, we'll know. If it's decayed into quiet plage by then, we'll see that too. The sun has patience. It doesn't care about our viewing schedule. What matters for the immediate future, for the next 48 to 96 hours, is twofold. First, the CMEs already launched from region 4419 are still traveling through the inner solar system, independent of whether their source region is visible or not. Those clouds will arrive, or not, regardless of what the sun is currently doing on its near side. They're already in flight. Nothing we do or see changes that trajectory. And second, the sun hasn't stopped producing active regions just because 4419 is leaving. Another one is rotating into view right now, a bigger one, more magnetically complex. And that's the real story of what comes next. Region 4420 is currently crossing the eastern limb of the sun, rotating into the Earth-facing side of the disk. Initial imaging shows a large, structured region with multiple sunspots, complex magnetic polarity, and a spot area that's been growing rapidly over the past few days. The classifications are serious. Beta-gamma-delta magnetic configuration, 20-plus sunspots, an estimated 250 millionths of a solar hemisphere in area. For context, that's a substantial region, definitely in the range where X-class flares are not only possible, but statistically likely. Let's unpack the beta-gamma-delta classification briefly, because it matters. Sunspot regions are categorized by their magnetic complexity. Alpha is the simplest, a single spot of one polarity. Beta is a pair, positive and negative, clearly separated. Gamma is when positive and negative polarities are intermixed in a more complicated way. And delta is the most complex. When you have opposite polarities within the same penumbra, the dark halo around a sunspot core. Delta configurations are where the magnetic field is the most stressed, the most tangled, and therefore the most likely to release energy as flares. A beta-gamma-delta region is one that has all the complexity markers at once. It's the classification that correlates most strongly with X-class flare production. Not every beta-gamma-delta region produces major flares. Some rotate across the disk quietly, but statistically, this is the configuration where the probability of something significant happening is at its highest. And region 4420 is rotating into the most dangerous position it can occupy, the part of the solar disk directly facing Earth, the central meridian, the place where any eruption is launched straight at us. Let's be concrete about what central meridian positioning means. When an active region is near the limb, its flares are angled mostly sideways. The CMEs head off to the side, away from Earth. The radiation is partially blocked by the solar material between us and the event. The geometry is unfavorable from the perspective of Earth impact. When an active region is near the center of the disk, the opposite is true. Its flares face us directly. CMEs are launched along the Sun-Earth line. Radiation reaches us with minimal attenuation. Every geometric factor that reduces our risk from a limb event increases our risk from a central meridian event. Same flare, same CME, same intrinsic energy, but the impact on Earth can be an order of magnitude different, simply because of where the event happens on the solar disk. Region 4420 is rotating towards central meridian over the next several days. If it maintains its current magnetic complexity, the probability of significant flare production while it's in the most Earth-pointing part of its transit is elevated. Forecasters are already flagging it. Flare probabilities for the coming week are running noticeably above baseline. M-class probabilities are into the 70 to 80% range on some days. X-class probabilities are 10 to 20%. These are not reassuring numbers. They're the numbers that make operators of sensitive systems start checking their contingency plans. And here's what that means in the context of everything else we've been discussing. The April 24th double flare from region 4419 happened from a region on its way out, at an unfavorable angle for Earth impact. If region 4420 produces comparable flares from central meridian, the geometry is completely different. Direct hits become the default, not the exception. Any CME it launches is aimed at us by default. Any radiation it produces reaches us efficiently. The story isn't ending. The story is escalating, and the setting is changing. Let me pull these threads together, because we've covered a lot. On April 24th, the sun fired twice from region 4419. The first forecast said the CMEs would miss. 12 hours later, the forecast was revised to allow for an Earth-directed component arriving late April 25th into early April 26th. The signatures of those flares, the shock speed, the Type 4, the 10-centimeter radio burst, the electron flux, all point to an event that was larger than the initial classification suggested. A previous CME from April 23rd was already in flight, creating the possibility of interaction between multiple clouds and an uncertain combined impact. Meanwhile, Earth experienced a slightly elevated day of seismic activity, which may or may not be related, and which honest science has not resolved. And now, region 4420 is rotating into central meridian, bigger and more magnetically complex than its predecessor, with elevated flare probabilities for the coming week. Any one of these, in isolation, would be a minor entry in the space weather record, but all of them together, stacked in the same narrative window, paint a picture of a sun in a particularly noisy phase of its cycle, producing the kind of events that keep forecasters busy and operational systems on alert. Nothing here is unprecedented. Nothing here is catastrophic, based on current forecasts. The expected impact from the April 25th, 26th arrival remains modest. G1 storm conditions, auroras at high latitudes, minor fluctuations in weak systems. Nothing that should alarm anyone who isn't directly responsible for satellites or power grids. But the setup is different than it was a week ago. The sun is producing back-to-back active regions. The forecasts are being revised in real time. The signatures are stacking. And the most dangerous position on the solar disk, central meridian, is about to be occupied by the most magnetically complex region currently visible. That's not a forecast. That's a situation worth watching, a situation worth understanding, a situation that, depending on what region 4420 decides to do in the coming days, could become something much larger, or could quietly decay into nothing at all. Both are possible. Both are on the table. Here's what I want to leave you with. This isn't one of those stories where I tell you something apocalyptic is coming, and you should be terrified. It isn't. The forecast is modest. The expected impact is minor. You should not be losing sleep over the April 25th, 26th arrival window. If you're at high latitude, check the aurora forecast, because you might get a good show. If you're not, nothing about your daily life is likely to change. That's the honest version. What I also want to leave you with is this. The sun is not a background object. It's not a constant. It's a variable star in the middle of its active phase, doing exactly what variable stars do. Producing events that challenge our models, revise our forecasts, and occasionally remind us that the space between us and the nearest star is not empty. It's a medium full of charged particles, magnetic fields, and shockwaves, constantly interacting with the planet that hosts every human being who has ever lived. Most of the time, that interaction is invisible. Once in a while, it becomes visible, and we get to watch the machinery in action. The forecasts shift, the signatures stack, the regions rotate, the CMEs travel, and the next one always is already on its way. This event, the April 24th double flare, the revised forecast, the coincident seismic activity, the emerging region 4420 is a window into that machinery. Not a crisis, a window. If you're paying attention now, you're seeing something most people never bother to look at. The real state of our relationship with the sun. This isn't the event. This is the setup. And the next 48 hours decide everything.